Hey gang, welcome back to 3440. Today we're going to talk about scatterplots and correlation. Scatterplots are another type of way that we like to visualize data, and it's an important one that's used in something called regression analysis that you'll probably do in a later course. So this is just kind of a little lead into that and some of the basic terminology stuff. So we're going to talk about those, and we're going to talk about one other type of plot that's related to a scatterplot that is sometimes useful. Okay, so let's talk about scatterplots first. So suppose that we have a real estate agent that wants to study the relationship between the size of a house and its selling price. All right, those would be the two variables we would be interested in. Okay, so it is reasonable to suspect, and we would suspect this in general, that the selling price is related to the size of the house, right? Because the bigger the house, the more it costs. So specifically, we would expect that the houses of larger sizes that are more likely to have higher selling prices, just in general. There are more factors that go into it than this, but this is a simplistic way to look at it. Okay, so a good way to visualize this relationship is with what we call a scatter plot. All right, so in a scatter plot, each individual in the data set, in this case the homes, all right, in the description I've given above, contributes an ordered pair of numbers. And each ordered pair is plotted on a set of axes. All right. So I've got that data set here on the next page. And so in example 1, the following table does present the size in square feet and the selling price in thousands of dollars for a sample of 8 houses in a suburban Denver neighborhood. All right. So I've constructed a scatter plot for this data. We're not going to do these by hand, obviously, but you can see on the x-axis here, I've got the sizes in the square feet. And on the y-axis, I've got the prices. And so this point right here, for example, represents this first point here in the data set. So that's 25, 21 on the x, and 400 on the y. So each one of those represents each one of those rows of data there. This is usually x, and this is usually y. All right. And so I want to show you how to get your calculator to do that real quick, just in case you haven't done this in a course before. I know some of you have, but if you haven't, the directions are pretty much here. So that data set we saw on the previous slide, to get that graph that you see depicted on the screen on your calculator, you're going to press the stat key and put your data in the list editor here, under edit, like we've been doing with other things. But you're going to put your x values in list 1, your y values in list 2, all right? And then we're going to go to the, make sure our scatter plot option is turned on in our stat plot menu. So hit second the y equals key and go to plot 1. Let's turn it on. And the very first option you see there is the scatter plot option. All right, that's the one you want. Mine's already chosen. You want to need to make sure your x list is your list 1 if you put your x values there, and the y list is your list 2, or whatever list you may have put your y values in. All right, it doesn't have to be list 1 and list 2. You've got other options there. And then we do zoom 9, and we get our scatter plot, and it looks quite a bit like the one we see on the screen over here. So pretty simple. All right, so you can do that with any scatter plot. All right, just in case you have to look at one. And we'll do this with other technologies. We'll learn how to make them in Minitab, and we'll learn how to make them in R. R is a little not hard to make them in, but there's a little bit more bells and whistles there. But when I say that, what I'm saying is that in R we have a lot more options of things we can do to make our graph look the way we want. As you probably have noticed in some of the ones I make, I typically like where I have the horizontal lines going across at the tick marks to kind of show it all the way across. I kind of like that view. It gives your eyes a way to gauge easier how close to the tick marks on the y-axis those things fit. And so there are features like that you can add here. Minitab doesn't have as many bells and whistles in that regard, and some other platforms don't either. You might be able to do some things like change the color of the points and things like that. But other than that, you get the same kind of graph. But we'll talk more about that later. Just know we can create it with just about any technology we want, or software. All right, so scatterplot description is very important, and it's going to be the bulk of what we really talk about here in this lecture. So when in that house size versus price scatterplot we created, we probably observed that the larger sizes, larger house sizes tended to be associated with the larger prices, right? Like for example, these guys up here, right? Those are the larger in square feet footage. Therefore, they're the most costly, right? So, and then the lower house prices tend to be associated with the smaller sized houses, right? And so we get this nice linear increasing trend of the points. They're not perfectly on a line, but we call when they increase that way on average as we go from left to right. When we go from left to right here, and the points get higher on average as we go from left to right, that's representative of what we call a positive association. Okay. In addition, the points tend to cluster kind of close to that what I call a regression line. That's what this is a regression line. And I'll show you how to get that on the calculator here shortly. But the closer those points are to that line, the more linear associated they are. All right. And so therefore we can say that this particular scatter plot has a positive linear association. All right. That's not the only type we have. We can also, as we just saw, we can define if the points kind of fit kind of close to a semblance of a straight line in an upward fashion from left to right, then we can say they're positively associated. All right, so larger values of one variable tend to be associated with larger values of the other variable, and the lower ones tend to be associated with the lower values, and that's what happens here. And so we call that positively associated. As a matter of fact, that's a positive linear association, really. If two variables are negatively associated, then the smaller values here tend to be associated with larger values here, and then on the other end, the larger values here tend to be associated with smaller values here. So they're going downward and on downward trend, almost like so. All right, so and those are kind of clustered together, getting close to a straight line, but not perfect. But they have a negative linear association in this case, or they're negatively associated. All right, so two variables, as you probably already said a couple of times, have a linear relationship if the data tend to cluster or close to or around a straight line. Now that should be taken with a grain of salt. Do they have to be really close to the line to be a linear associated? Not really, but they need to have a trend where they're kind of moving in towards a line that you would draw on the graph, all right, a straight line. We also have what we call a weak association. So you can still have somewhat of a linear trend as the points in this graph here for the weak association have. There's still somewhat of a linear trend going up, but notice the points are kind of pulled a little further away from this line I drew as opposed to the ones that on the previous slide, which were closer to the line I drew. All right, so when they start to pull away more or get more what I call a scatter shot, or a good best way I've ever heard to describe is like shotguns shot into like a piece of sheet metal from a certain distance will spread out really far from each other. And so the more scattered your points are, the more weakly associated they are. And so the more nebulous your cloud of points are, you have a weak association, which is, means that our points are not going to tell us as much about our data, the association of our data, as we would like them to. So that's not always a good thing. All right, so the weaker the association, the less information we can get, basically. We also, the last two types of descriptions, and these aren't the only ones, but these are the main ones, are what we call a nonlinear association. And that's probably pretty evident here because you can see that these points are either curving in an upward fashion. So the points are getting larger over time, but they're curving. They're not really in a straight line. And so we call this a positive nonlinear And when they kind of curve in more of a downward trend, or the points are getting smaller as we go from left to right but curving, then we call that a negative nonlinear. Okay. So let's double check our concepts here. So for each of the following scatter plots, let's state the type of association that's being exhibited. So I'm looking at A first, and A's got a downward trend. The points are trying to pull together there. They look like they're kind of pulling together on themselves in a straight line. So I would call this a negative linear association. Scatterplot B is curving quite strongly, and it's not a good thing that it's curving. Let me take that back. Strike that comment. When data curves, it just means it's not linear, but it doesn't necessarily mean it's bad. All right, in a scatter plot, you would prefer to have a linear association, because when we do in a regression class, when you do linear regression, if your data is more in a linear fashion, you get better information and stronger information from it. When it curves, there are other types of regression you can do for curved data that will still allow you to do regression, but they get measured in a little bit different way, which we're not going to get into here. But this one's, since the points are curving up in this particular case, we're going to call this one positive nonlinear association. C looks like a pretty nice little conglomeration of points trying to fit towards a line, almost like that. All right, and so this would be a positive linear because it's not curving at all. E, I'm skipping over D for a minute, is kind of doing a downward curve, so the points are getting smaller as we go from left to right. So this is a negative nonlinear. And then D is a weak association, mainly by process of elimination. Weak linear. I couldn't decide if I tried which direction I want to draw that line in. The points are so much in more of a nebulous cloud that they're not pulling together, and it's hard to tell whether this would be a negative weak linear association or a positive one. And so it's kind of hard to tell. Therefore, we're just going to call it weak linear. I mean, because you could almost imagine drawing a line this way or this way, and it would make just as much sense, honestly. So it's hard to tell with weak linear associations which direction the line would actually be drawn in without actually performing regression on it. But when it's weak like that, like I said, the information we get, we can still do things like regression to it, or we can do other things with that data set. But the reason we do regression to begin with is to make predictions about stuff in the future using this data that we've collected like this. So the more linear it is, the better our predictions are. The weaker it is, the weaker our predictions are, and they're less reliable. And so we don't like it when things are really weak. All right, we're going to come up with a nice measurable to determine when things are truly weak linear versus positive and negative linear, okay? Or how strong the relationship is. Matter of fact, we're going to talk about that right now. The correlation coefficient is that exactly. So when two variables have a linear relationship, we really would like to have a measure of how strong that relationship is. So a numerical measure of the strength of the linear relationship between two variables of interest is known as the correlation coefficient. Okay. So the correlation coefficient is if the data set, for example, that we've been using so far with the house size versus the price are considered ordered pairs. So we had 8 ordered pairs that we plotted, right? So given those ordered pairs, we can find the sample means x bar and y bar, the sample standard deviation s of x and s of y for each group. So this would be like in the house example, our x values were the size, right, of the house, and the y values in this case would be the prices. So we'd find for each one of those, we treat them like separate little mini data sets, and we'd find the mean of the sizes, the mean of the house prices, and the standard deviations for each one of those things, and then the sample size. And the correlation coefficient could be calculated using this formula right here. Now there are several different versions of these formulas out there. These are two that you'll see fairly regularly. There's a third one out there that gets used in regression courses themselves when you know a little bit more information about some other things, which we won't get into in this class. But I will say, out of the two, I like the second one better than the first one because it doesn't require us to find the mean of each variable and the standard deviation of each variable. They're kind of fit into this second formula, and all we have to do is find certain values, like the sum of the x times the y values, the sums of all the x values in the x list, the sum of all the y values, the sum of the x values squared. So we square the x values and then add them all together, and then the sum of, then we square all the y values and add them all together. We need those 5 values, and we can plug in this formula and be done. All right. This first version here, this guy here, requires a little bit more of a table style of calculation. So you'd have to like go through, take each value in your x list, or in this case like the house pricing one, the size value, and subtract it from its mean, and then divide it by its standard deviation. So you have to do that for each one of those x values, and so you have to get a whole column of x values, subtract from their mean, divided by each one divided by its standard deviation. Then you have to do the same thing with the y values in another list. Then you multiply all that together, and then you get the sum of those multiplications. So it's a little bit more tedious process, and that's why I don't really like the first formula as much. The second formula, though, I want to show you how you can use that in just a minute, but let's talk about the correlation coefficient and some of its properties first. So the correlation coefficient will always be some value between or including -1 and 1. So that is our correlation coefficient value falls between -1 and 1 and can include or be -1 and 1. All right. The correlation coefficient does not depend on the units of the variables. So in other words, the correlation coefficient is just a measure of strength. It doesn't have a unit. All right. So it doesn't matter if for example, we can take and compare, not really compare, but we can have two different variables with different units on them, like price and square footage, as in the house example, and it won't matter. The correlation coefficient has no units associated with it, so we don't have to worry about that. It doesn't matter which variable you choose as x and which one you choose as y when you're doing this calculation, because it's going to come out the same either way. The last two bullets here are kind of important and things we're going to talk about a little bit more in a little bit. But the correlation coefficient only measures the strength of a linear relationship. All right. So it can be misleading when that data set, when that relationship is nonlinear. So when we get a nonlinear scatter plot, that's a bad thing. We don't like that. All right. So it can be misleading when that happens. The correlation coefficient is also very sensitive to outliers. So an outlier on a scatter plot, a point that stands out well above and beyond all the others on the scatter plot, can also be misleading, and so the correlation coefficient shouldn't be used in those cases either. Okay, we're going to see an example of what happens when you have an outlier and pull one out here in a little bit. So let's go back and let's calculate the correlation coefficient using that second formula that we saw a few pages back, this one here. So we're still using the size and prices here of the house prices, and we need a couple values here. So I need n, which is easy to figure out because over here in the data set we've got 8 rows. 8 rows of data, right? And so n equals 8. We don't need the calculator or anything to tell us that. But we need a couple of other things. We need the sum of x times y. We need the sum of the x values in that list. We need the sum of the y values in that list. And then we need the sums of the squared x values. And we need the sum of the squared y values. If we have those things, we can do this formula pretty much justice. Notice in the formula too that these are just the sum of x and sum of y. Once we have those, they're squared. When you take prop stat, you'll probably learn why this formula looks this way. These are basically here another way to calculate the s of x and s of y values. without having to actually directly utilize the standard deviation formulas, the traditional standard deviation formulas. Okay. So in the calculator, though, we can get these values and these sums really quickly. So I already have my data set in stat in list 1 and list 2. So I've got that. If I go and hit stat again, okay, and then go over to calculate, and then go down to 2 var stats instead of 1 var stats, I'm treating list 1 and I want its information about it and list 2. So it does this does what 1 var stat does, but it does it when you have 2 columns of data. Okay, so in this case list 1 and list 2. So when I pick that, my data's in list 1 and list 2, so I don't have to change the X list and Y list. And I just need to go down and hit calculate. When I do that, I get the same information I would from 1 var stats, but I'll get it for both sets of both columns of data. But what's nice about this is I get the sum of X, which I need, and the sum of X in this case is 23,130. Right? I get the sum of X squared next, which I need, which is 67,383,000, or 67,383,000. If I look down here towards the bottom, I get the sum of Y, which is 3576. And if I scroll down, I should get the sum of Y squared. The y value squared, 1604640, or really 1,604,640. And if I keep scrolling down, it will actually give me the sum of X times Y. It's almost like they knew we needed these values for a specific reason. So scroll back up there, there we go. So I get, it's like 10,389,541. Okay. So now I can actually use those to calculate R. So R, let's see if I can draw a straighter line than that real quick. We get 8 times the sum of X times Y, which is 103,89541, minus the sum of X, which is 23,130, times the sum of Y, which is 3576, all over the square root of N, which is 8, times the sum of X squared, which is that 67,383,000, minus the sum of X value, which is 23,130, all squared, and then that's going to be multiplied times, and I'm going to run out of room, so I'm going to have to go to the next line. That's 8 times the sum of Y squared, which is the 1,604,640, minus the sum of Y squared, or sum of Y quantity squared, which is going to be 3576 squared. That's all underneath the square root still. Putting the line over like that. And so R should equal approximately 0.90059175526. So it's still a little bit of a tedious process, but not as bad as the other method that I didn't show you. But usually we round the values to 3 decimal places, and that's usually good enough. So 0.901 would really be the final answer here. But there's an easier way to get this out of your calculator, and I'm going to show you how to do that, I think, next. I am. So to get that same value, and we'll talk about what that value represents here shortly, you have your data, you put it in list 1, list 2, but if you've never performed a regression on your calculator, you need to make sure that what we call your stat diagnostics is turned on. There are 2 ways to do it. You can do it if you have an 84 that's fairly modern, you can do it under the mode key, because it's down there on your list under mode, under stat diagnostics. Some of you may have to go to, may have double pages that you have to go down all the way and find it. But you want to make sure that wherever it says stat diagnostics, you have it turned on. All right. Mine is already on, so I don't need to do that here. But if you don't have an 84, you got an 83, the only way to turn the stat diagnostics option on is to use the catalog. And this can be done on any TI calculator. So if you hit the catalog button, is the option 0 here, or the 0 key, and catalog's right above it in blue or yellow, possibly on a TI-83. So if you hit second and the 0 button, you bring up the catalog. Now the catalog is in alphabetical order, and so to find what we call diagnostics, we have to go, it's not going to be stat diagnostics, it's just going to be diagnostics. To find diagnostics, we're going to find the X inverse key because the letter D is above that. We're going to hit that or click on that button, and it'll bring us down to the D's, or the beginning of the D's. You can't do anything further than one letter here, just in case you've never done this before. But you got to scroll down till you find diagnostics. They have off and they have on. It's better just to have them on. If your battery ever dies in your calculator, it will automatically revert back to off, so you may have to turn them on to get your correlation coefficient. That's the reason why we're doing this. And just hit enter once you picked on, and hit enter again, and it's done, so it's turned on. Okay, what I'm trying to do is get, when I run the regression, to get my screen to look exactly like this last one down bottom here. Okay, so now if I go to stat, since my data is already in my list 1 and list 2, if I go to stat and go over to calc and then go down to linreg a plus bx, you could technically use linreg ax plus b2, but number 8's more for a stats class. We choose option 8, make sure we have list 1 and list 2 here, and skip the freak list, you don't need that. If you wanted to plot your regression line on top of your scatter plot, you can do that here if you want. You can do that under the vars key by pressing vars at this point while you got your cursor here under store regression equation, and then go over to the y vars option once you hit vars and pick function, and then choose y1. This will put your equation, your regression equation, in y1, the y1 slot for your graphing utility, and then just go down and hit calculate. It gives you the correlation coefficient, and this is how I expect you to probably do it on the midterm. If I ask you to find this value, use the calculator, it's just quicker. But there we get the same value. If we round to 3 decimal places, 0.901. Okay, and we also get the regression equation. If I hit the graph button again, it will go ahead and automatically draw that line there, because in the plot area, what we're under the y equals key, if you press that, you'll see that it's placed that regression equation there for us. Okay, so it's plotting that for us. So anyway, that'll give you a good measure of how close to the line your points are actually fitting. Okay. This is not to be confused, by the way, with the normal QQ plot, because the normal QQ plot is about assessing normality. A scatter plot is about assessing how strong your linear relationship is between what we call bivariate data, or where you have x values and y values on a plane like this. While technically a QQ plot does look a lot like one of these, it's not exactly the same thing. All right, they're similar in some ways and very differently used, and very differently used. Okay. All right, so that's how you can get one of those guys. How you can get the correlation coefficient on your calculator. So what about interpreting the value? So we got 0.901 for our house data, right? So 0.901 was our correlation coefficient for R. So how do we interpret that? Well, interpreting the correlation coefficient, here are the rules for that. So if R is positive, then the variables have a positive linear association. So since R value is positive, we know we have a positive linear association, so 0.901. If R had been negative, if it was negative 0.901, then we would say it had a negative linear association. All right, so far 0.901 actually falls here. If R is very close to 0, then the association is weak. But 0.901 is way closer to 1 than it is to 0, so we don't have a weak association here. But the closer R is to 1 or negative 1, the more strongly the linear association is. So since 0.901 is really, really close to 1, we would say that we have a strong positive linear relationship. So the I'm just going to say relationship, REL. Good Lord, come on, eraser, go away. All right. Now the last caveat here, the last bullet says that if R equals 1 or -1, then the points lie exactly on a straight line. So yeah, if you ever do regression or do try to find the correlation coefficient, and that value ends up being 1 exactly or -1 exactly, then the points fall on a straight line. If R is exactly 1, then that means all your points fell on your graph in a perfectly straight line, and they all fall on the line. Or sorry, that's the -1. But conversely, if all your points fall on perfectly on a straight line, ascending upwards, and R is probably 1, you have a perfect positive slope of 1. And if they fall downward, let me change that to red real quick. 1, 2, 3, 4, or so, however many points you got, they all fall in a straight line, then R is probably -1, and they all fit directly on the line. This doesn't happen very often unless you fix your data to be perfect somehow, but in nature this very rarely happens. So when two variables are not linear related, though, the correlation coefficient does not provide a reliable description of the relationship between our variables. In short, what I'm saying is if your data is nonlinear or has an outlier in it, then we can't use the correlation coefficient to accurately describe our data set, our relationship. So that's something to keep in mind as well. All right. As a matter of fact, what happens when we have an outlier in there? Remember we talked about a statistics being resistant. R is another type of statistic, and it's not resistant to large or small values or extreme values in general in a data set. So in this plot here, which compares area of land versus the farmland in a state in various states, in a sample of states here, Alaska stands out and is an outlier from everybody else because all these other points kind of stick over here in a line, right? But that's not where our regression line would fall if we actually did regression on this thing. Because that outlier being present there, the correlation coefficient for the plot turns out to be -0.119, which is very weakly associated, but it's misleading because most of the other points kind of have a linear trend, right? But that one outlier is kind of pulling that away and causing our correlation coefficient to become weaker, all right? So it's not giving us a true representation of the rest of the points in the graph. That outlier is affecting everything else. And so we're being misled. But if we removed Alaska and said, well, Alaska doesn't have a lot of farmland anyway, why are we comparing it with all these other places that have farmland, a lot of farmland? Then removing that guy causes our correlation coefficient to be R equals 0.710, which is a much stronger relationship when we ignore that outlier. So sometimes in this case, it is permissible to remove the outlier in cases like this. Still should be done very sparingly, the removal of outliers, but it is in this case it might be okay to do, depending on what the other states are in your sample. If most of the other states are states with a lot of farmland in them, but they're smaller states, and then you're bringing in Alaska, who's a huge state with very little farmland, you're not really comparing anything of importance here because maybe Alaska's not maybe known for that particular part of agriculture. So we could probably throw that one out. So the base point here, outliers are bad. We can't use the correlation coefficient to aptly describe a data set when it has an outlier present. So which of the following scatter plots is the correlation coefficient an appropriate summary? Look at A first. I'd say that the correlation coefficient would be an appropriate summary of this data because there's no outliers in this data set and there's an increasing trend. So I'd say that it is appropriate, or R is appropriate. B, the data is curving pretty bad. This is nonlinear data, right? When the data is nonlinear, it makes sense that a value that we use to describe the strength of a linear relationship does not work. Therefore, R is not appropriate here for summarizing this data set, or the shape of the strength of the linear relationship here. And then last but not least, plot C has an obvious outlier in it, right? Therefore, that outlier is going to construe our correlation coefficient, so R is not appropriate here because of that outlier. Okay. So you kind of want to keep an eye out for those for things that happen like B and C, and then go, well, I can't really use the correlation coefficient in those cases. If we throw the outlier out in C, we probably could, though. It just depends on what that data represents. All right, last thing, one of the last things I want to talk about here is correlation versus causation. So let's look at an example for this. So an economist discovers that over the past several years, both the salaries, so there's our one variable, of U.S. college professors and the amount of beer consumed in the U.S. have gone up. So there's a positive correlation between the average salary of college professors and the amount of beer consumed. So the economist concludes that the increase in beer consumption must be caused by professors spending their additional money on beer. Let's explain why this conclusion is not necessarily true. Are they correlated? Yes. We could calculate the correlation coefficient between the salaries and the amount of beer, and if those things have gone up over time and show a positive linear trend, we're going to get a positive correlation. Okay. But can he assume because the professor's salaries went up that the amount of beer consumed in the entire United States has gone up as well? That professor salaries rising actually causes that? That the truth is no, because there's a lot of other factors in there. We're talking about the population of U.S. professors, and then the other variable here is the amount of beer consumed by the United States, the entire population. That's probably not a good way to go about saying that just because they're correlated implies that that one causes the other one to occur. If the other variable had been amount of beer consumed by college professors only, maybe we could make that jump, but still we'd have to be cautious of that. Correlation does not imply what we call causation, and so that's the basic rule of thumb here, is just because the average person on the street, sometimes they'll run a study like this or they'll read something like this and they'll go, oh, well, this must be due to the fact that the college professors are making more money, so people are drinking more beer. Oh, that makes sense, but it doesn't really. So that's the thing we want to think about. In general, when two variables are correlated, we can't always conclude that changing the value of one variable will cause the true change in the other variable. Mathematically, that may happen from the data we have, but it doesn't mean that one truly causes the other. And so don't conflate correlation and causation. They're not the same thing. Just because things are correlated doesn't mean one causes the other. A better example of this, and a more ridiculous example of this, is let's say one of our variables was the number of shark attacks during certain months, or for each month of the year, and the number of and the amount of ice cream might be the other. So let's say X was this, and Y was the amount of ice cream sold. In a given month, on average. During the summer months, we'd expect shark attacks and the amount of ice cream sold to increase, right? Because it's warmer weather. People are more likely to go to the beach, be in the water. Therefore, shark attacks could increase at that point in time. And sharks are more active during warmer weather as well. And then the amount of ice cream sold usually goes up when the weather's warmer too. But just because those are correlated, and they would be highly correlated, doesn't mean that the number of shark attacks causes people to spend more money on ice cream. That's just not how that works, and so therefore that's another good example of that correlation does not often imply causation. So just keep that in mind. Okay. The last thing I want to talk about are bubble plots. All right. So this is these are similar to scatter plots. And we either some people call them bubble plots, or a bubble plot, or a bubble chart. A bubble plot is a type of graph that we use to display 3 dimensions on a 2-dimensional graph. And when I mean 3 dimensions in this case, 3 variables, because in the house example we did, we were looking at 2 variables, right? The size of the house versus the price of the house. So those were 2 dimensions, or 2 variables. So in a traditional scatter plot form, that would show just those 2 dimensions. But this is one of the few acceptable ways to show 3 dimensions on a 2-dimensional graph or a 2-dimensional page. Unlike the 3-dimensional bar graphs we saw, which are bad because they're hard to read, these are not as bad to read, and they also kind of give us additional information. And so this is a good way to show 3 dimensions. So in this type of plot, 2 of your variables will be represented on the x-axis and the other on the y-axis. And the third variable will be represented by either the size or the area of the bubbles, or the points on your plot. So the bigger the value, the bigger the bubble. The smaller the value, the smaller the bubble. And so I redid the house price study, and I added in the lot size in square feet, so the actual property size. So we have still the house size and the prices on the x and y axis. So those are the two variables there. So this looks very similar to the plot we've seen earlier. But I've added in the size of the bubbles represent how big the lot size is in square footage. And so this gives us a little additional information. I mean, for example, this one house right here specifically, that cost the house is a little bigger than 3,000 square feet and costs somewhere around $470 or so $470,000 or so. Is the lot size is not very big. It doesn't have a very big yard, so we get information about the yard here. The one closest in price to it, though, has a lot size, a much bigger yard, and the price isn't that drastically different. So it's that's a big difference in square footage of a yard. It's somewhere between 8,000 to 8,500 square feet in the lot size. So it's given us a good indication about how big these the sizes are, and we can see other things in there too, which are nice. This gives us a lot more information. Another one I made just to show you guys is this one right here, which is from a data set in R. And both these graphs were created in R, by the way. But it's the state population comparison in 1977. And on the x-axis, we've got the high school graduation percentage, so the high school graduation rate, essentially, or the percentage of folks who passed or graduated high school in those states that year. Or had graduated from high school. And then the income per capita, and if you're not sure what that is basically the entire state's income divided by the population, which is why these values aren't huge on this, somewhere between 3,000 and 6,000. And then the size of the bubbles represent the actual size of the population. So this is a very useful model here to get a good gander on how do you compare states across one another and how they're performing. And so we can kind of see there might be an outlier up here. I don't know that I would call it one specifically, but Arkansas has the highest high school, or close to the highest high school graduation percentage. Utah has a little bit higher one there. But it definitely has the highest income per capita. But notice that its bubble's pretty small, so its population is just maybe slightly bigger than 300,000 people in 1977. And that may be 300,000. That 300,000, they didn't give us the units in this data set, unfortunately, which upsets me a little bit. So I don't know if that's 300,000 people or it's 300 people per square kilometer or what. They didn't give that information. But nonetheless, we can still tell that population is pretty small. Okay, and then we can compare that across different things, which is nice. In R, you can make your points kind of like translucent a little bit so that you can see through them to see other points, like Florida's hidden in here somewhere, and they were about mid-grade there for both high school graduation and income per capita. And so we can kind of still see those things, but we can see here a couple, like in the scatter plot, we can still see there's an increasing trend as you go from left to right here, which is important. So there is a relationship. Okay, going on between this. Looks like South Carolina, and I've seen this plot in different formats before, and I knew South Carolina was low end on the high school graduation percentage that year, and also not the lowest in income per capita, but not far from being one of the lowest ones. And so, and Georgia surprisingly falls here as well. Still better than most of the other southeastern states. And actually, when you look at it, you see a lot of states from the southeast in this thing. So you can almost there's a lot of things you can see in a bubble plot. They can tell you a story based on the type of variables you use to create them with. And I'll try to give you guys a link in the announcements at some point that I recommend everybody watch by a gentleman named Hans Rosling. It's a YouTube little clip of him using a bubble plot to show how the history of the world has changed versus income per capita, the average age of death versus the population of certain areas, and he does it over over 100 years, and so it's like telling a good story. So bubble plots are really great for visualizing data and telling stories. So I actually like them a lot. They're one of my favorite types of plots. So anyway, we'll show you how to make one of these later in the semester. These will not be on the midterm. The bubble plots won't, but everything prior to the bubble plots will be on the midterm. So there's no quiz on those questions. So just make sure you can calculate the correlation coefficient and know how to describe them and things of that nature. Okay. I hope you guys are having a great one, and I'll talk to you later.